Hello, my name is Kathleen Pareish. This is Cade Secor, and this is our Project 2 presentation for BMEN 351. So the housing market plays a very important role in the economic state of a country. Specifically, the volatility of housing prices can directly affect the economic stability. So drastic changes in those housing prices are not good. So it's important to have accurate housing prices because if the prices are accurate within one specific area, everything will be standard and very stable. And so that will increase the economic stability of that area. So the current method for determining the listing price of a house is to use a real estate agent. So they will look at similar houses, they'll use their past experience and better judgment to determine the list price of a house. This isn't the best method considering that it can change a lot between person to person, and these aren't like super scientific methods. So one study has been done that has compared three different learning methods, machine learning methods, to determine the listing price of a house. And then there was also another study done that used a linear regression model to determine the list price of apartments in Dubai. So our data set was collected from Zillow.com, and we tried to use data parsing, but it was unsuccessful. So we hand collected 150 samples from postings that looked similar to the ones below. In a lot of cases, the lot size was reported in square footage, so we had to convert it into acres. And collecting data this way took a very, very long time, so we were only able to collect 150 samples, and this obviously limited the accuracy of our model, but the more we collected, the better it did get. The features that we collected were number of bedrooms, number of bathrooms, square footage, acreage, year built, zip code, price, and then one front-facing image of the house. Everything except the image was used in a linear regression model, and then a separate model was made just for the image. And this is our data set. The left side is the data set in Excel, and the right side is it in a Pandas data frame. So we took all of those features I mentioned before and we put them in a correlation matrix. And as you can see, there's correlation between all of the features and price. So we kept everything. And here are the histograms and the distribution of every single feature. And these specific 5 features, you can analyze their distribution. Bedrooms, bathrooms, square footage, and price all have a right skewed distribution. This makes sense when you think about it because houses that have a lower price, lower square footage, those are going to be more common because you can build more of them. Houses that are like over $1 million or have a very high square footage, they're not going to be as common because they're less accessible for the general population to have. However, the year built, we did try to have more recent houses in that information because the more recent the houses are, the more applicable this data set and our model could be for actual life. And here's our exploratory data analysis. For the year built and the zip code, we decided to use the most common value rather than an average. And then for the image ID, there wasn't really a statistic we could analyze because this is simply just a placeholder for the name of the image file. And then we did alter our images for use in the image model. We rotated them, we did a width and height shift. We made sure the axis was oriented correctly. We did shear and zoom. And then we used an input function imported from Keras for image preprocessing. And we also scaled and normalized the images for use in that image model.
So for our baseline, we decided to look at the mean house price of the overall data set. Essentially, we compared the mean overall to each individual price. Because it's a linear regression model, there's not specifically a categorical accuracy, so we decided to look at other metrics such as R-squared score or the correlation or coefficient of determination, mean squared error, mean absolute error, and mean absolute percentage error. The values for our baseline mean house price are displayed below. Now for training, we initially started with a split of 80% training and 20% test. Then for the purpose of getting validation data, we further split up the training data into 80% true training and 20% validation. This resulted in overall 64% training, 20% testing, and 16% validation. Our final model was evaluated and trained over 40 epochs. The loss and accuracy plots are displayed below. Essentially, we utilized early stopping regularization, which resulted in only 36 epochs being used, but these models do demonstrate underfitting. Our initial model was just one image model based on a sequential transfer learning model with a convolutional MobileNet v2 base. No custom layers or hyperparameters were added. We simply took in the MobileNet v2 base, applied it to the image, and ran it. Generally, there was not much of an improvement from the baseline. Here's a summary of the model. So moving towards our final model, we had one linear regression model for the table data, and then the separate sequential neural network model with a convolutional base for the images. And then we combined them for the overall. We implemented freezing the fine tuning until the 100th layer. We added max pooling and convolution in order to decrease dimensionality, detect patterns, and improve overall robustness of the model. This resulted in a total of 7 layers, which can be seen off to the right with their shapes. This is the appropriate model summary of the image model specifically. So the image model that we described before and the linear regression model were combined into another linear regression model to result in what you see here. We have a residuals plot off to the side that compares the actual prices with the predicted prices. Generally speaking, most of the predictions were relatively close. Only about a third of the predictions were not accurate. And then looking at table 3 off to the left, you can see there's significant improvement in our final model with a 96.7% difference in the mean squared errors and a 21.5% difference in the mean absolute percent error. And then a total compilation of all of the metrics used in all of our models is displayed in table 4. Some key takeaways. Essentially, the housing market plays a very important role in economics. Data parsing through Beautiful Soup was unsuccessful, so housing data had to be manually collected from Zillow. This definitely affected our model. Baseline was calculated based off the mean of the housing price data. The final model used 2 models, one linear regression model and one sequential neural network image model with a convolutional base, and was combined into a final overall linear regression model. The initial was just the sequential neural network without any extra training added. The final model was the sequential with max pooling convolution, early stopping regulation, and much more. Overall, the model improved from the baseline by 96.7% for mean squared error with regards to percent difference in the values and 21.5% for mean absolute percent error. Overall, the model is successful and could be used in applications for predicting list pricing of houses.
So for future work, a feature that we could look at adding is the depreciation of the house. Basically, this would be the square footage of the house multiplied by the year built, and we would use this in place of the year built feature. And then this model could also be applied to broader categories such as the appraisal process. This specific process possibly led to the 2008 financial crisis. And if we were able to improve upon that process and make it more standardized, then we could avoid those crises. And here are references. Thank you.
Thank you.